What if rockets could be built as quickly and efficiently as electric cars? What if the future of space travel didn't depend on slow, handcrafted engineering, but on high-speed industrial production? Deep in South Texas, something extraordinary is taking shape. A massive new facility known as Star Factory is redefining how spacecraft are built, and it could permanently change humanity's path to the Moon, Mars, and beyond. This isn't just another factory. It represents a bold shift in philosophy. Build fast, test fast, improve fast. Instead of producing a handful of rockets over many years, the goal is to manufacture them at a pace the aerospace world has never seen before. The ambition is staggering. Hundreds of starships, potentially even one per day in the future. Before we dive deeper, I'm curious about you. If you're excited about this kind of breakthrough and want more content like this, comment 1 below. If this topic isn't really your thing, comment 2. I genuinely want to know what you think. Because what's happening here isn't just about rockets. It's about transforming an empty stretch of coastline into a high-tech hub. It's about rapid growth, economic shifts, bold dreams, and real controversy. From experimental tents to a mega-scale production complex, this is the story of how industrial speed may unlock the next era of human exploration. In the beginning, there was no massive factory, no towering assembly bays, no streamlined production lines. The earliest versions of Starship were built inside large temporary tents set up in the wind-swept landscape of South Texas. It was an unconventional sight. Stainless steel rocket sections rising from muddy ground, engineers working under fabric roofs, prototypes rolling out into the open air for testing. It looked more like an experimental workshop than the birthplace of the most ambitious spacecraft ever designed. But that was exactly the point. At that stage, nothing about Starship was final. The design was evolving almost weekly. Each prototype introduced changes, different weld techniques, structural adjustments, updated engine configurations. Failures were frequent and very public. Explosions during landing attempts, structural collapses, and rapid disassemblies were part of the learning curve. Instead of hiding setbacks, the team embraced them as data. The temporary tents allowed maximum flexibility. If something needed to change, they could modify the process immediately without being locked into rigid infrastructure. This phase was chaotic, but it was strategic chaos. As testing progressed, patterns emerged. The design matured. The shift toward what became known as Starship V2 marked a turning point. The vehicle's dimensions stabilized, structural reinforcements improved reliability, and key systems became more standardized. With greater design certainty came a new challenge: speed and scale. Building rockets in tents was no longer efficient enough for the vision ahead. That's when the concept of Star Factory was born. Instead of a scattered experimental setup, the goal became industrial precision. A permanent, enclosed facility would allow controlled manufacturing conditions, better quality control, and far higher output. Heavy machinery replaced improvised setups. Automated welding systems improved consistency. Sections of the rocket could now be fabricated in parallel rather than sequentially. What once took weeks could now be done in days. The transformation of the surrounding area was just as dramatic. What had once been a quiet, isolated coastal stretch began to resemble a rapidly expanding industrial hub. Massive steel structures rose from the ground. Assembly buildings grew taller and wider. The now famous megabay structure towered over the flat terrain, capable of stacking rocket sections at unprecedented heights. New storage tanks, cryogenic systems, and engine test facilities appeared almost overnight. Housing developments followed. Roads expanded. Infrastructure multiplied. Engineers and workers poured into the region. What had started as a remote experimental outpost was quickly becoming a full-scale aerospace production center. The evolution from tents to Star Factory wasn't just about upgrading buildings. It reflected a deeper philosophy shift, from experimentation to optimization. The early phase proved that rapid iteration could work. The new phase aims to industrialize that speed. Instead of building a few test vehicles each year, the mission is to build dozens, eventually hundreds. This journey, from flexible improvisation to structured industrialization, mirrors the broader ambition behind Starship itself. First, learn how to fly. Then, learn how to build at scale. Because reaching other worlds won't just require powerful rockets. It will require the ability to produce them again and again, reliably, efficiently, and faster than ever before. If the early Starship prototypes were experimental drafts, Starship V2 represents a decisive leap toward a production-ready spacecraft. It is not a minor upgrade. It is the result of years of testing, failures, redesigns, and engineering refinements, each lesson carefully folded back into the vehicle's structure. One of the most noticeable changes is its size. Starship V2 stands slightly taller than earlier versions, creating more internal volume for payload capacity and system integration. But the real advancements are not just in height, they are in resilience and precision. The nose section, once considered a vulnerable point, has been significantly reinforced. During earlier test flights, heat exposure during re-entry posed serious challenges. Thermal tiles loosened, structural areas overheated, and engineers had to rethink how the spacecraft would survive repeated atmospheric returns. In V2, the heat shield coverage has expanded, especially around critical stress zones. The nose structure is stronger, better insulated, and designed to withstand extreme re-entry temperatures with greater reliability. The forward flaps, crucial for aerodynamic control, have also been redesigned. Previously, their hinge systems and positioning created mechanical stress under dynamic loads. In the new configuration, the flaps are reshaped and repositioned to improve leverage and stability. The geometry provides better control authority during descent while reducing structural strain. The result is a vehicle that can maneuver more predictably during its dramatic belly flop re-entry profile. The aft section has undergone equally important upgrades. Shockwave pressure during atmospheric re-entry once introduced heating concerns and vibration stress near the engine bay. Starship V2 incorporates structural refinements to mitigate those forces. The base is more robust, improving the protection of the propulsion system during both ascent and descent. Thermal protection remains one of the most complex engineering challenges. Earlier flights saw tiles detach, exposing vulnerable steel underneath. In V2, installation methods have been improved for tighter tolerances and stronger attachment. Automated placement techniques within the factory environment enhance consistency. This reduces the likelihood of tile loss and increases confidence in full reusability, one of the core goals of the entire program. Structurally, the stainless steel rings that form the body have been optimized. The welding process is more precise, producing smoother seams and greater uniformity. Weight reduction has been carefully balanced against strength requirements. Every kilogram saved increases payload potential, but durability cannot be compromised. V2 reflects a more mature understanding of that balance. Perhaps most importantly, the Raptor engine configuration has been refined. The layout improves performance efficiency while simplifying integration and maintenance. Engine reliability is critical, especially if the long-term vision involves frequent launches and rapid turnaround times. Starship V2 is more than a better rocket. It represents a shift from experimental testing toward scalable production. Each improvement reduces uncertainty. Each refinement increases the probability that Starship can fly repeatedly, land safely, and be prepared for its next mission with minimal downtime. In essence, V2 moves the concept closer to what it was always meant to become: a fully reusable spacecraft capable of supporting missions to orbit, the Moon, and eventually Mars. It is not the final version, but it is a powerful step forward in transforming an ambitious idea into an operational system. Building a powerful spacecraft is one challenge. Building it at scale is an entirely different one. The true ambition behind Star Factory is not just to create advanced rockets. It is to manufacture them in quantities the aerospace industry has never witnessed before. The initial production target is bold, up to 100 Starships per year. That translates to roughly one new vehicle every 3 to 4 days. In an industry where a single rocket can take months or even years to assemble, this represents a radical departure from tradition. But even that number is only the beginning. The long-term objective is even more aggressive, eventually reaching a pace of 1 Starship per day. Why aim so high? The answer lies in scale. A single mission to Mars is not enough to establish a permanent human presence. If the goal is to build a self-sustaining settlement on another planet, transportation capacity must increase dramatically. Thousands of tons of cargo, habitats, life support systems, machinery, food supplies, energy infrastructure would need to be delivered. Transporting people alone would require dozens, if not hundreds of flights over time. Estimates suggest that building a city on Mars could require around 1,000 Starships operating over a decade or more. That level of logistical movement demands industrial-level production. Without mass manufacturing, interplanetary settlement remains theoretical. With it, the timeline compresses. In the near term, these vehicles would not only serve Mars ambitions, they are also expected to support lunar missions, cargo transport to orbit, and large-scale satellite deployment. Programs focused on returning humans to the Moon rely on heavy lift capabilities, and Starship's payload capacity makes it central to those plans. High production rates ensure redundancy, faster iteration, and the flexibility to support multiple missions simultaneously. There is also an Earth-based vision. Rapid point-to-point travel across the globe using suborbital trajectories could reduce intercontinental travel to under an hour. While still conceptual, such a system would only be feasible if spacecraft were produced efficiently and at lower cost per unit. To reach these production targets, expansion is essential. A second large-scale manufacturing facility is planned to complement the original site, increasing total output capacity. Multiple factories working in parallel would create a distributed production ecosystem, reducing bottlenecks and accelerating delivery timelines. This shift toward aerospace mass production may redefine the economics of space access. When rockets are produced in larger numbers, costs can decrease through repetition, learning curves, and process optimization. More launches become affordable, more experimentation becomes possible, more players can participate. The ambition to build 100 or eventually hundreds of Starships annually is not simply about quantity. It is about transforming spaceflight from rare and extraordinary into routine and repeatable. If achieved, it would mark a turning point in human capability, the moment when reaching orbit, and perhaps other worlds, becomes industrialized rather than exceptional. Just a short drive from the launch site lies Brownsville, Texas, a historic border city that, until recently, moved at a much quieter pace. For decades, it was known more for its coastal charm and deep cultural roots than for cutting-edge aerospace development. But the rapid expansion of Starbase has changed that dynamic in ways few could have predicted. On the positive side, the economic impact has been undeniable. The arrival of large-scale aerospace manufacturing brought new jobs, engineers, technicians, construction workers, logistics specialists, and service staff. Local businesses have seen increased demand. Restaurants, retail stores, real estate agencies, and contractors have all benefited from the influx of workers and investment. Infrastructure improvements followed. Road expansions, upgraded utilities, and renewed attention to public facilities. Perhaps most importantly, opportunities that once required young residents to leave the region are now appearing closer to home. For years, Brownsville faced a brain drain problem, where top students pursued careers elsewhere and rarely returned. The presence of a major aerospace operation has begun to reverse that trend. Technical education programs are expanding. Interest in STEM careers is rising. For many families, the idea of building a high-tech future without leaving South Texas now feels possible. Downtown revitalization has also gained momentum. Investments in community spaces and local development initiatives have contributed to a sense of renewed energy. Property values have increased, and new housing projects have appeared to accommodate incoming workers. However, rapid growth rarely comes without tension. Rising property values can benefit homeowners, but they also push rental prices higher. Some long-time residents worry about affordability and displacement. As demand increases, the cost of living shifts, and not everyone experiences the benefits equally. Economic transformation can create opportunity, but it can also widen gaps. Environmental concerns are another source of debate. The surrounding area includes sensitive coastal ecosystems and wetlands. Rocket launches generate noise, vibration, and potential debris. Increased industrial activity alters landscapes that were once largely undeveloped. Conservation advocates question the long-term ecological impact and call for careful monitoring and regulation. Cultural change is also part of the conversation. Brownsville has a strong local identity, shaped by generations of families and cross-border heritage. The influx of a new workforce, many arriving from other states, introduces new dynamics. Some residents welcome the diversity and modernization. Others worry about losing aspects of the community's traditional character. In many ways, Brownsville's experience reflects a broader pattern seen when major industries move into smaller regions. Growth brings momentum, optimism, and financial activity. It also introduces stress, uncertainty, and adjustment. The development near Starbase has transformed more than just a coastline. It has reshaped the trajectory of a neighboring city. For some, it represents long-awaited economic revival. For others, it raises important questions about sustainability and balance. The story of Brownsville is not simply about progress or resistance. It is about navigating change in real time, as a global ambition unfolds right next door. Star Factory is more than a manufacturing facility rising from the Texas coastline. It represents a turning point in how humanity approaches space. For decades, rockets were rare, handcrafted machines, built slowly, launched sparingly, and treated as extraordinary events. The vision unfolding now challenges that model entirely. It suggests a future where spacecraft are produced at industrial speed, where launch becomes routine, and where access to space expands beyond what once seemed possible. The transformation of a quiet coastal region into a high-tech production hub reflects something larger than infrastructure. It shows how quickly the future can materialize when ambition meets execution. From experimental prototypes assembled in tents to a massive, optimized factory targeting unprecedented output, the evolution has been dramatic, and it is still ongoing. At the same time, the ripple effects remind us that progress is complex. Economic growth, technological breakthroughs, environmental responsibility, and community identity all intersect in this story. The path forward will require balancing innovation with sustainability and opportunity with accountability. If the production goals are achieved, the implications are profound. Regular missions to orbit could become common. Lunar operations could expand. The long-envisioned journey to Mars could shift from distant dream to structured plan. Industrialized spaceflight could mark the beginning of a multiplanetary chapter in human history. Whether Star Factory ultimately fulfills its boldest promises remains to be seen. But one thing is clear. It signals that the era of experimental possibility is giving way to scalable ambition. And that may redefine what humanity believes it can achieve next.